All right, so welcome back. Today we're going to continue on functions. Remember last time we went through functions in both languages. Remember we are on Piazza and YouTube, so if you have any questions, go ahead and post there. Otherwise, just to remind you of what we did, we ended on modularity, right? So in C, modules meant that you were separating things out into header files and source files, and then compiling them one by one. We gave a full demonstration on that. So that's what you'll be doing from now on in your lab this week and everything following. And remember that it can get quite complicated to compile stuff. You'll have dependencies upon dependencies upon dependencies. And so if we ever have any occasion to give you a complicated enough code like we would do in your labs and your hacks in the coming weeks, we give you a make file for doing this. I don't know that we repeated that step in the Java versions of the lab because basically it's all opaque. That the IDE, Eclipse, is taking care of all of that behind the scenes for you. So you don't really have to worry about it, but in a more complex project in a Java, you would use a build system like Ant or Maven or something like that. Okay? So what I want to talk about today is how do these functions actually work? And for that, we're going to start taking a look at, we'll go ahead and start with C here. All right, so first of all, let's go ahead and go over this demo here. And I'll preface this by saying, never write functions like this, right? Add, multiply, and then a sum of squares, right? Those are terrible functions because all they do is add two numbers, multiply two numbers. You already have operations to do that. But what I wanted to do is I wanted to start out with something simple so that we're not focusing on what the actual code does. What I want to do is I want to focus on how the code is actually working, okay? So let's go ahead and run this, and you'll see that it calls these variables on A and B, right? And so what's the sum of squares? 10 squared is going to be 100. 20 squared is going to be 400, so the sum should be 500, and we're good, right? What I want to do, though, is I want to visualize this. So I'm going to go ahead and take this code and come over here to a tool called Python Tutor. It was originally written for the Python language, but of course it has support for multiple languages. And so again, what we have here is sum squares, which is a function, and sum squares calls multiply, and add, right? So how is this actually working? Let's visualize this execution. It might take a couple of seconds here. But basically we have function calling function, right? So hopefully it doesn't take too long. There we go. All right, now this is a tool that you're free to use if you want to. Again, you can go to pythontutor.com. But what we can do is we can step through this and visualize what our code is doing, right? So you can see over here that I've got this thing called a stack. I wonder what that is. And later in the semester, we've got this thing called a heap. We'll talk about that later. Main has what's called a stack frame. It's just like a picture frame. It is framing everything that is relevant to the main function. In this case, argc and argv, those are parameters to the main function. A and B and C, these are all local variables to the function. I didn't provide any command line arguments, so this pointer variable here, we'll talk about pointers later today. They've used the poop emoji here to as a little joke to indicate that it's an uninitialized pointer, right? But otherwise, after lines 20 and 21 here, I've got 10 and 20. Now I'm about to call sum squares. As I do this, observe what happens. A brand new stack frame is created called sum squares. Sum squares has two parameter variables, A and B. And then it has two local variables, S and T, that it's going to use to store the values that are returned from this multiply function. So at this point, I'll call your attention to how many variables called A and B we have. How many do we have? Two, right, of each, right? There is one in this stack frame over here. There's another in this stack frame over here. In fact, when I go into it and start executing this, you see that 10 and 20 have been passed into the function. Those are not the same. They hold the same values, granted, but they are not the same variables. Remember when we talked about scoping, right, where a variable is visible? Well, these are stack frames. You're only allowed to look at one picture frame at a time. You look in one picture frame and you see A and B. You look at a different picture frame and you see a different A and B. Right? So let's go ahead and continue here. Some squares will end up calling multiply on line 13, which creates yet another stack frame, right? With A and B in it. Again, A and B are the parameter variables here. There are no other local variables because all it does is compute A times B, and it returns the value. So you can kind of see that these stack frames are growing. Now, in this visualization, unfortunately, they're growing down. But I'll show you a different visualization here that's more common to show you that they're growing up. It really doesn't matter because you can take your computer and you turn it upside down. Does the computer care which way is up or down? No. It's just a bunch of hardware, it's a bunch of wires and electricity. And they don't care what's up and down. It's just a way to visualize something, okay? Now, once we got 10 and, we passed in 10. So 10 for both A and B here, A and A. So A and B, now it's clear, hopefully, that now I've got 3 variables named A and 3 variables named B, but they're in completely different scopes, they're in completely different stack frames, all right? Now, when I go back, when I hit next and I return this value, 10 times 10, 100, what's going to happen? What happened to that stack frame? Did you see it? I'll go back one step. What happened to that multiply stack frame right here? Poof, right? It got destroyed, right? That's called popping. We'll talk about the terminology here in a second. Why? Because it returned, right? That function called a function, called a function, and once that function was done, it returned back to the calling function. Let me step back one second here. How do you know what function called what function? Main called sum squares called multiply. These are called breadcrumbs, right? Why would they be called breadcrumbs? Does anybody know? Everybody knows the fairy tale Hansel and Gretel, right? You laid breadcrumbs to go into the forest. You don't know your way. Why? So that you can find the breadcrumbs on your way out. So how do we return back to the calling function? We just pop that stack frame, destroy that stack frame, and now we're back in the original function. And we can continue and call multiply again for on B, 20, 20, multiply those together, destroy that stack frame, and then ultimately return back to, or I guess we're calling add now. All right, and then 100 and 400 get added, and then finally we return from add, and then we return from sum squares. Now we're back in main, and we can print it out, and you can see the 500 up here. Right? This is how functions actually work. Okay, we have what's called a program stack. So what is or a call stack? Sometimes people call it. A stack is a LIFO data structure. That's LIFO stands for last in, first out. Right? Now, before we go on, why is it called a stack? Think about real life. Think about a stack in, say, a cafeteria. A stack of dishes, okay? What is that stack? It's a nicely organized pile of dishes, right? When you go to grab a dish so that you can go and get your food in the cafeteria, which dish do you grab? The one on top, right? Now, the brave of you or the truly helpless may try to grab the dish on the bottom or somewhere in the middle, right? What's going to happen if they do that? They're going to fall, right? Don't do that. Now, suppose that you've washed your dish. Where do you put the dish? Onto the pile of clean dishes. You go and wash your dishes, and where do you put it? On the top, right? Those two operations are called pushing onto the top and popping off the top, okay? And literally, I've not looked at the history here of why they called these stacks, but I literally think that it was because of dishes. When you push something onto the top, now, in the actual cafeteria, when you put the dish on the top, you don't have this tall stack of dishes, do you? What is the mechanism by which you can put a dish in and take the dish off? It's down here, right? And there's a spring-loaded mechanism that pushes the dishes. You put the dish on and then you push it down and then it holds the dish, right? That's literally where I think it comes from. You push the dish onto the top, pushing down the entire stack of dishes. Right? Popping off the top, I have no idea where pop comes from. Pop, I don't know, you pop it off the top. But I think that goes back to the 40s or 50s on when they gave these things names. Remember, there are only two difficult things in computer science: cache invalidation and naming things. So when they said, okay, well, we've got this concept of a function calling function, and these frames with local variables. Well, it looks like a stack of dishes to me. Okay, well, that's what we'll call it, stack of dishes. Now, what do you do when you push a dish on top of the stack in the cafeteria? Well, you push it. Okay, great. Now, where did pop come from? I have no idea. You'd have to go back and talk to those folks in the 40s and 50s that came up with these terminologies. But anyway, a stack can be used to keep track of breadcrumbs. This function A calls function B, calls function C. How do you get back to where you came from? Well, this call stack gives you the breadcrumbs of where you came from. What function called what function? It's keeping track of all that information. So to backtrack out of the forest, Hansel and Gretel, assuming that their breadcrumbs didn't get eaten, all you have to do is go backwards in the breadcrumbs that you left, right? Each time a function is called, a new stack frame is created and pushed on top of the call stack. Each time a function returns, the topmost one is popped off the top, right? Each stack keeps track of all of the local variables, parameter variables, and return values, just as we saw in this visualization over here. The parameter variables are kept track of, all the local variables are kept track of, and then there's a special thing that's not visualized with this code or with this visualization tool, but the return value. When we return 10 times 10, we needed to put that somewhere. So there's usually a return register or a return piece of memory that is specifically set aside for the return values. Right? So each stack frame keeps track of all that stuff. Okay? As a consequence, every stack frame, here, let me get this out of there. There we go. All right. Every stack frame's variables are separate. Right? We have a variable A over in that stack frame, a variable A over in that stack frame. That's how function scoping actually works, by keeping track of separate variables. Now, when it actually gets compiled, the variable name A, the variable name B, those are gone, right? The computer doesn't care what you called your variables. It just has these abstract notions of this memory address and that memory address, and they're different. And I store one thing in that thing and one thing in another thing, right? So all those variable names are gone anyway when you actually compile something. Every function has its own scope and its own stack frame and its own variables. This is how we keep things nice and separate, okay? But unfortunately, that has a consequence. What I want to do is I want to take two variables A and B, and I want to swap them. I don't want to run, of course I could do this locally if I wanted to, but I want to write a function to do that, okay? So let's go ahead and write a function to swap those two variables. It's going to be a void function because it's not going to return anything. It's going to take A and B, and it's going to try to swap them around so that it's B and A. So I'll call it swap, int A, int B. Right? Now how do I swap variables? I need a temporary variable. I need a temporary variable and do what with it? All right, put A into temp. Now what? A is now free, right? So I can put B into A, and now B is freed up. I can go ahead and put temp into B. All right, let's print the fact that we received 10 and 20 in this function, and let's print the fact that we've swapped them in that function. What I'm going to do down here is I'm going to print them before 10 and 20, which we would expect, and now let's call this swap function, swap A and B. Okay? And I'm going to hold off on this last print statement here, and I'm going to let you guess what's going to happen. All right, so, oops, I want a GCC swap. There we go. So on the first print statement, it's 10 and 20. The second print statement, which is inside this function, is 10 and 20. We swap them around on lines 7 through 9, and indeed, A and B have been swapped, 20 and 10. Now, when I print them down here, what would you expect? Would you expect 20 and 10 because they've been successfully swapped? No, why? In fact, they haven't been successfully swapped. These variables are not the same A and B as these variables up here. Yeah, you swap those parameter variables, but those parameter variables are different. And again, you can visualize this. Let me go back over here, edit this, and put in the swap demo here. Hopefully it doesn't take too long. Okay, let's run through this code. We've got 10 and 20, right? Then we print them out, great. We call this swap function, but A and B are different variables. Indeed, I am going to go through and swap them so that it is now 20 and 10, but when I return, did you see any changes to A and B, the original A and B over here? Nope. No. Right. Now, hopefully this becomes abundantly clear if I were to change these variables, x and y. Right. Now, if I were to do this, and I need more changes here, but if I did that, it would be absolutely clear that x and y are not the same variables as A and B. Right. I don't think I need to go that far here, though. Yeah?
Is it not good practice to name like variables and things?
These are just toy examples anyway, so you definitely want better variable names, but
Is it right to name them the same thing?
it's perfectly fine for one function to name whatever the hell you want in that function, whatever you want in that function. They're separate, so why should they care that, hey, you have the same variable names as me, so we can share, right? As long as they're good variable names to begin with. Now, this is just A and B, X and Y, they're just numbers, so this is a toy demonstration here. So if it were real, you'd want better variable names anyway. Okay. Here's another visualization of the stack. It grows upwards. When your program actually executes, the entire program code is loaded on the stack at this bottom here. Then you've got global variables and static content. Like say, if you print out hello world, that string hello world is static content that does not change, and so it gets loaded up into the program stack. Then if you've got main, and main calls, and these are different, this is a different example, but main calls average, average calls sum, right? You have a different stack frame upon different stack frame. Now it looks more like dishes, right? Because the top, it grows up. You have a new stack frame on a new stack frame on a new stack frame, etc. Function calling, function calling, function calling, function. And this is how we can keep track of that stuff. Whether or not it's low memory or high memory, that completely depends on the operating system and the compiler and all that stuff, right? In fact, again, it's just a way to visualize it, that it grows upwards. Over here in this visualization tool that we were using, Python Tutor, it was growing downwards, right? It doesn't matter. You'll find that trees, in real life, trees grow up, but in computer science, trees grow down because trees represent data. And how do we read? Do we read up? Nope, we read down. Down, top to bottom, left to right. So weird things happen, right, in computer science. Don't worry about that just yet. So the consequence here is that this is passing by value, right? In most programming languages, including C and Java, right, variables are passed to functions as pass by value. What does that mean? The value of the variables are copied into the parameter variables. Right? The original variables are completely different because they exist in completely different stack frames. Only copies of the values are passed to the function. Consequently, you cannot swap them, but sometimes we want to. Sometimes you do want to pass a variable instead of the variable's values. right? Variable's value. In this case, it's singular, right? This is known as pass by reference. Right? A reference is a memory location, okay? What I'm talking about here is instead of copying 10 and 20 and giving the copies of the values to you and putting them into your variables, I'm the calling function, you're the function now. What I'm going to do is I'm going to tell you, oh, there are these two variables called A and B, and they're located in that memory location over there, and the second one is located in that memory location over there. And what you can do is that function that you just called says, okay, great, I know how to jump to that memory location, and I can consequently make changes to it. Right? Take a look at how memory is actually stored in a computer. All memory has an address and contents. So when I forget about the pointers here for a second. When I create a variable, an integer variable a, it's stored somewhere on the system using some sort of a memory address. It's all completely opaque to us. This is just a hexadecimal representation of it, right? Who cares what it actually is? It's kind of meaningless to us anyway, because at the end of the day, it's probably running on some virtualized machine and virtual memory that has virtual memory on a virtual cloud server on top of whatever. There's going to be like 5 layers of abstraction. Is this really actually a physical memory address on your wires in your computer? Probably not. But it's a way to access something, just like a house. A house has a bunch of numbers on it. It has an address. What's stored inside that house, the family that lives there, that's its contents, right? So the value 10 over here is the value of A, and its address is over here. So when I pass in by value, what I'm doing is I'm copying the value of the variable 10. When I pass by reference, I'm passing this memory location, so that the function can jump to that memory location and grab the contents, change the contents, do whatever they want to do with the contents of that memory. All right? But in order to do this, we need pointers first. All right? So again, every piece of data in a computer is stored in memory. Right? Memory consists of an address, that is the location, and its contents, the actual data stored. Right? In C, not in Java, in fact this is almost unique to C, you can create a pointer variable that points or references an actual memory address instead of say an integer value. Right? To create a pointer variable, you use the star symbol, right? And we'll just call this star, right? So let's go ahead and go into code mode here, and let's look at creating a pointer variable. So here's a regular old variable declaration. Right? Int a is equal to 42, right? Is this large enough for everybody in the back? Okay. All right. How do I make a pointer variable to an integer? Right? Int star ptr to a. That star makes the difference. That star means that it's a pointer that can point to a memory location. Now, at this point, what does ptra point to? What? Ptr, or ptra, 2a, sorry, is a pointer variable that can point to any memory location that holds an integer. Usually, how many bytes is in an integer? 8 bytes? 8 bits in a byte. What? Okay. So, some background here. I believe in the C standard, an integer has to technically be at least 2 bytes. But usually it is 4 bytes, right? Because you need 32 bits to represent a 2 to the 31st minus 1 integer value, which gives you that 2.147 billion. The last bit is used, or actually the first bit is used for the sign bit, 0 for positive, 1 for negative. But usually, in the vast majority of systems, it's going to be 4 bytes. Right? A long or a double is going to be, why do we call them doubles? Because it's double the size, right? A long is going to be, I've run out of fingers now, it's going to be 128 bytes? Or 128 bits. 128 divided by 8 is what? 16, right? So 16 bytes, right? Something like that. I don't know. But it really depends on the system, right? Usually it's going to be 4 bytes, though. Right? In general, or at this point in the code, what does PTR2A point to? Nothing? Good. But there is, in C, there is a difference. There's a difference between nothing and something else. So let me go ahead and put this into the visualization here. And let's find out, oh, you know what, I think it's going to end up compiling this away, unfortunately. Yep, it is. So because I never actually used the pointer variable, the compiler is getting rid of it because it's a useless variable. So let me actually do something with it. Do not pay attention to what I'm doing right now. Right, line 11, never do something like that. There we go. I forced it to keep that variable because I did something with it. So let's go ahead and go through these lines. 7. Pointer to A. What is it pointing to? This question mark here. Right? The question mark is not nothing. Nothing is 0, void, null, right? And we'll talk about null here in a second. Otherwise, what is it pointing to? No idea. If I created a regular old variable, int b, what value does b have right now? Not necessarily. It's a crapshoot, right? It could be 99% of the time it's going to be 0. But it could be whatever dead beef was there before. Remember that term, right? And so it's an uninitialized variable. It has the C standard says there's no, I don't know, right? What does it point to? Who knows? Right. It is undefined. And unfortunately, undefined behavior is undefined behavior in C. Anything can happen. In fact, there's a C implementation that is completely 100% compliant to the C standard. But in the event of any undefined behavior, what this compiler in the system will do, it will erase your hard drive. And so it's a joke. Nobody would actually use this in practice, but it's a tool used to indicate to tell you that undefined behavior is undefined behavior. Don't rely on something happening because anything could happen. Anything, including deleting your entire hard drive. Right? Or launching nuclear missiles or something like that, right? All right, so who knows? It's undefined. Right? Yeah, go ahead. Yeah, I forget what it's called. Is it, or is it, that's something different. Suicide Linux. What happens? Yeah, I mean, there are legitimate uses for something like that. Sometimes mistype. Okay, so this one appears to be hyphen rm rf everything from the root. What if you do any bad command? That'll happen. Okay, if you get any bad command or wrong command, you do that. Sometimes you want that though, right? If you want to, if somebody's raiding you, right? Do suicide Linux would be. All right, do that one command that will erase everything before they get to it, right? And so it's kind of like what's called a dead man switch, right? That you're holding on to the button. That's what's preventing the bomb from going off. The second they tackle you and you let go, then it all explodes, right? And so it's a way of keeping people away. It's a dead man switch, right? And there are legitimate uses for that, not just mad bombers, right? All right, so in general. Oops, let me go back to the notes. It is best practice to initialize a pointer to something. Right? So if you don't know what you want it to point to, you initialize it to null. Null is a special keyword that is defined in the standard library. So I guess it's not technically a keyword. I think it's probably a preprocessor directive. But it's all caps. It is not the same thing as null. That is used in Java. It's not the same thing as null with a capital N. It is all caps in C. Okay? And you can use this, right? You can say in C, I will set int star ptr to a is equal to null. There we go. There. And then you can check for null later on, right? If ptr to a is equal to null, then printf, don't use the pointer. Right? Bad things will happen. Right? If you try to use that null pointer, then in C or in Java, you've probably seen it before. The message comes up, null pointer exception. Right? What happens in C when you try to use memory that doesn't belong to you? So do you remember? Hopefully everybody did it at least one point, unless you absolutely listen to everything I say, right? And you had scanf. Maybe you forgot the ampersand. What happens when you forget the ampersand? It breaks. How does it break? With a? What is the message when your program quits? A segmentation fault, right? You're trying to access a segmentation of memory that doesn't belong to you or that doesn't exist, like null. Null is yet another way of expressing nothing, right? Okay, so you can check for null and, looking before you leap, basically. To make a pointer point to an actual variable, you need the memory address of that variable. Right? To get the memory address of a variable, use the referencing operator. Right? And let me highlight that. Referencing operator. And that referencing operator is going to be the ampersand. You've seen that before. Scanf, right? I told you it was magic at the time, and now we're going to understand what that means, right? So here we go. What I'm going to do is ptr to a is equal to ampersand a. Let me finish it up there, right? And now it points to a, right? Now ptr to a actually points to a. Right? Careful. Right? You don't want a pointer to point to an invalid memory location or a location or one that does not belong to your program. Right? For example, the following are invalid. Right? The following are invalid. Sorry, it's not scrolling for some reason. There we go. The following are invalid. If I tried to make ptr to a point to 42, right? Or if I tried to make ptr to a equal to a, right? Both of those are invalid. A is a regular old variable. 42 is a regular old integer value. Right? PTR to A is a pointer, a reference to a memory location. Right? So let's go ahead and take a look and see what the consequences are of doing that. I'm going to go over here to the demo and get rid of everything that we've done. Don't worry about that. I've got A, right? And I will create a PTR pointer to A, and I will try to set it equal to A. Pointer variables are declared with that star value. Okay? Now what I'm going to do is I'm going to print out information about it. Printf. PTR to A, or A, is stored at memory location %. Now %D formats an integer. %F formats a floating point number, a double. How do you think I can format and %C is the only one that makes sense. It formats a single character. This one also makes sense. So hint, What letter do I use for a pointer variable? P, right? And so A is stored at memory location with value %D and the line. So how do I get the memory location of A? Properly, it would be ampersand A. And how do I get the value stored at A? It's going to be just regular old A. Right? Printf. But the pointer points to memory location %P. Right? And we'll go ahead and print out PTR to A. Let's go ahead and run this. GCC demo. And I'm already getting a warning about this. It's not an actual compiler error. It's just a warning. Hey, you're mixing pointers and regular old variables. I don't think that that's what you want. This is the same basic error that you would have gotten if if in scanf you'd forgotten your ampersand. So let's go ahead and run this and see what we get. A is stored at memory location blah 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 blah. Right? Is that meaningful to us at all? It's just a memory location that's being stored on some virtual machine, on a Docker instance, on Amazon Web Services cloud somewhere, right? So that's just a memory location that belongs to us, but it's kind of meaningless. And it has a value of 10. But the pointer points to memory location 0xa. These are hexadecimal numbers, base 16. So you have 0 through 9 and A through F. Don't worry about the hexadecimal. You don't need to memorize it or anything like that. But 0xa, that's the value of 10, right? How do we know that that's the value of 10? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? I've got 0 through 9. Now I need to increment 1, 0 if it were base 10. But what's the next symbol if I use 16 symbols? 0 through 9 and A through F. What's next? A. There it is. Right? Now, what if I try to do something with that memory location? What if I try to say, print out what's there? Here's a preview of what we're going to talk about next, PTR to A. Right? What this is a dereferencing operator. Right? So there's a referencing operator, gets you the memory location of a variable. To go backwards, you use the star again as a dereferencing memory location. So let's find out what happens, with value %D. Right? There we go. All right. So again, the same warnings as before. What's going to happen now? Does the memory location 10 in all likelihood even exist? Does it belong to me? I don't think so, right? The likelihood that it belongs to me is extremely slim. So what happens when I try to access memory that doesn't belong to me? Segmentation fault. Okay? So make sure that you are pointing them to valid memory locations. Okay? Again, putting an ampersand in front of a regular old variable gives you the memory address of that variable. You can manipulate the contents of it through its pointer. So let me go ahead and use this now. All right, here. Yeah, I'll just cut and paste this whole thing right here. All right. So I've got int a is equal to 42. Of course, I can always reset its value to be 17 using a regular old variable. But I can also make my pointer point to that variable, and then I can make changes to it. Now, PTR to A, that's a pointer variable. So how can I take a pointer variable and change it into a regular old variable? I dereference it because it's already a reference. It's a memory location. I put a star in front of it, and the star operator turns it into a regular old variable. And now you can put 30 into it. So let me go ahead and go back over here and do this properly. There we go. So A is stored at memory location %P. And here I'm going to go ahead and put in PTR to A because now it's properly pointing to A. And we can change it. A is, let's go ahead and change its value. PTR to A is equal to 42 now. Now, is that correct? PTR to A is a pointer variable. If I make it equal to 42, where does it point? To memory location 42. Right? So I need the asterisk or star, right? You can call them asterisk if you want to, but that's kind of a mouthful of star. A is now stored at the same memory location, but now it has a different value. I changed its value through its pointer. Right? And you can see that same memory location, right? And its value has now changed to 42. By the way, if I run this one more time, would you expect that to be the exact same memory address? No, why? It's changing every single time. Remember how, oh, I guess it's gone now. But remember how the stack works, the program stack? The program is loaded up into memory in some location. The likelihood that you get the exact same loading address when your program starts is extremely unlikely, right? It's going to be loaded up wherever the operating system thinks that it's best, right? Memory is being used and unused and given back to the operating system millions of times a second on modern computers. Right? So the idea that you would get a program loaded up in the exact same memory location, very, very unlikely. Java is a different story because Java it runs on a Java virtual machine. And one run of a Java program, it has no relation to the actual hardware below. It's all relative to the Java virtual machine. So it will be loaded up in the same, it could probably be loaded up into the same memory location, virtual memory location in Java. Right? Okay, those are pointers in C. What about Java? So this is really easy. Let's go back over here. Java has no pointers. In fact, very few languages actually do, right? You do not generally manipulate the memory contents directly in Java. Great, so it's easy. We can just skip everything, right? But by default, all primitive types in Java, that is int, double, char, the lowercase versions of all those things are passed by value. So as a consequence, if I have the same exact swap function over here, is it going to end up swapping them? Here, this is Java now. I'm in Eclipse right here. It's not the only difference was I had to put system.out in front of everything. Right? So 10, 20, we swap and then we print it out. When I run this, you're going to get 1020, 1020 in the function, in the method. 2010, we have swapped A and B, but down here, we end up swapping, we end up not swapping the originals, right? These are passed by value, right? How do we end up passing by reference? Right? That's something that I'll demonstrate here in a second and see. All object types, say string, uppercase S, integer, double, etc., are passed by reference, but generally all built-in types are immutable. So have you talked about immutability before? No? All right, let me go ahead and do a demonstration over here then. I'm going to go ahead and get rid of this stuff. So string S is equal to hello. Oops. Oh, you know what? I made a mistake. I meant for that to be a capital H. Okay. S is equal to hello. Oops. Now this is Java. Can I do that? Sure. System.out.println S. And you can see before the change and after the change, it indeed works. There we go. So did I change that string though? What I'm going to do is I'm going to show you that I didn't change that string. String T, before I do this, I'm going to make a reference to S. Okay? And then what we're going to do is we're going to print out S and T before the change and S and T after the change. Okay? Now, I don't have the same visualization. You can have the same visualization tool over here. This is pythontutor.com/java.html, and then you can look at it this way. Actually, let me do that. I'll go ahead and grab this and put it over here in my main and visualize this execution. Oh, duh. There we go. And this is superfluous. There we go. All right. Ignore that. So let's walk through this code. Well, main, come on. No? There we go. S is the lowercase h hello. Okay? There is a memory contents that stores that thing. T is a reference over to S. And unfortunately, it's not actually showing this visualization as as it should, as a reference. When I print them out, of course, I get hello and hello. But now I'm changing S. Did I change T? Nope. That's an old version of the function. Unfortunately, darn it, this is a terrible visualization of this because it's not how it actually happens. This line right here, 5, is basically making T reference back to the original lowercase h-e-l-l-o. And when I say S is equal to uppercase h-e-l-l-o, I'm not changing S. What I'm doing is I'm making S refer to a different memory location with different contents. Okay? And again, unfortunately, it's not going to show me that visualization on this tool. I should have checked it out beforehand. Simply because I don't know why they're not actually showing that these are references to memory locations. But anyway, Java has no pointers, but each one of these things is a reference. And they are passed by reference into functions, meaning that the memory address is being passed into the functions, but they're all immutable. What immutability means is that once created, an immutable variable's contents cannot be changed. You can't change a string in Java. You can only ever create a new string. You can't change that lowercase h to an uppercase h. You can only create a brand new string with an uppercase h and change your reference from S, referring to this string right here in memory, to referring to that string over there in memory. That's what it means in Java. Right? Immutability is a very good thing. Yeah, go ahead. It sits there in memory and does nothing until the Java, if there's no references to it, there's still T. T is a reference to it. But if I make T point to something else, and nobody is paying attention to this lowercase h hello anymore, then it becomes garbage. It's eligible for garbage collection. Then the Java virtual machine, when it deems fit, says, all right, I need to clean up memory. And all right, that's garbage. It starts picking up after us, basically. No, it's during runtime. Right. The compiler can compile away things that are not used. The compiler can look at your program and say, well, you don't use that, so I'm not even going to compile that. And that's optimization, but it doesn't do that in this case because I'm actually using it. I'm printing it, right? So it needs to create it. If I never used it, it probably wouldn't even end up, it might end up in this visualization, but a good compiler would compile it away. Okay? Immutability is a very good thing. If you cannot change something, then you have a guarantee that once you set it, nobody can change it. It means that everything is thread safe automatically, right? In Java, immutability provides automatic thread safety. All right? So think about your computers, your modern computers. My MacBook is now 5 years old, but I think it's got a quad core, and with hyper-threading, I can get like 8 processes running in parallel at the same time. I'm really wanting one of those M1Xs when they come out, because I think that you can get up to 16 processes at the same time.
Yeah, this is an M1.
Oh, well, that's an M1.
Oh, not
No, yeah, the X's haven't been released yet. Is that Air or is that 13 inch? Oh, that's a Pro? Okay. 13 inch Pro, right? Okay, because they don't have the 16 inches either, right? So, okay, do they? 16 inch M1s? I thought they were waiting for the M1Xs. Okay, anyway, you can probably run 8 or 16 processes at the same time, something like that, right? We live in a multi-threaded world. We live in a world where all of our processors now, nobody makes processors anymore that don't have multiple cores, where you can run multiple threads or multiple programs at the same time. In fact, that's the only way that we can get performance out of our hardware. Everything is as fast as it can be, basically, at this point. And so what you need is throughput. You want as many things running at the same time. So when you program something, you have to program something in the modern world, you have to think about parallelization, creating threads, creating processes so that 8 different things can run at the same time. We won't get into it in this course. I usually cover something like that in, say, 156 in the honors course, but you need thread safety. If one thread goes and reads data and another thread comes in and reads data at the same time, how do you know that they're not stepping on each other's toes? Well, if this thing is immutable, then thread B has a guarantee that thread A can't screw around with it. It's read-only. And if it's read-only, then you have thread safety immediately, right? Very, very good thing. It was built like that in 1995 before a lot of multi-core computers were out there, with the idea in the mind that in the future, all processors will be multi-core. The future today will everything will be threaded. Everything will be multi-core, and you have to program towards that. And so they built in thread safety from the ground up 26 years ago now. Right? Okay, that's Java. What I want to do, the last thing I want to do here is go back to C and now solve our original problem, the swap problem. Right? This didn't work. How can we make it work? I'll create another function here with a different name. Remember, we can't use the same name. Why? What is that called? Function overloading. Overloading. Truncation would be like the integer thing where you lose the fractional part. I'll call this swap by reference. Right? The original was swap by value. I gave it regular old variables. But now, instead of giving it regular old variables, I'm going to give it pointers. Now, A and B are memory addresses of integers rather than integers. Okay? Let me go ahead and get rid of the print statements here. Can I do this? Can I say temp is equal to A? The thing on the left-hand side is a regular old variable, right? The thing on the right-hand side, is that a regular old variable, A? Nope. So how do I take a regular old variable, or sorry, how do I take a pointer variable and turn it into a regular old variable? Star, right? Or asterisk, right? That's the dereferencing it. Dereferencing operator. It takes a pointer variable and changes it into a regular variable. Now these things are compatible. Likewise, dereference A, dereference B. Dereferencing means don't look at the address. I've got it still up here. Dereferencing means don't look at the address, look at the contents of the memory, right? Jump to that location and pull out its value and then jump to the memory location pointed to by A and put that value into that memory location. Yeah. Oh, okay. Yeah, I wasn't done yet. There you go. Because it's not permanent. It's just like a say int x, and then I go double x, right? For typecasting. It is only for the purposes of dividing by x or something like that. It doesn't change the variable. The variable is still a pointer here. Right? It just dereferences it, jumps to the memory location. Okay, now I've got the 10 or 20 or whatever. Right? Now let's try to compile this. GCC swap. And let's try to run it. Oh, you know what? Did I save? Oh, duh. Okay. Swap by reference. I need to change this. So now I'm going to swap to try to actually swap this. Now I should get a compiler at least warning, if not an error, right? Yep, just warnings. Right? What is it warning me about? It's warning me about A and B. A and B are regular old variables. Is that what swap by reference takes? Does it take a regular old variable? Nope, it takes a pointer variable. So now again the question, how do you take a regular old variable and change it into a pointer variable? A star? Remember, that's the dereferencing. Takes a pointer variable and changes it into a regular old variable. Ampersand. And ampersand. Now let's go ahead and compile this. And before it was 10 and 20. And on the previous version, it didn't change A and B because, you know, it was passed by reference, or passed by value. Copies of 10 and 20 were passed into the function. But now, does it work? 20 and 10 are successfully swapped. Another analogy that I like to use so that you can visualize this is, I didn't give you 10 and 20. All right, I'm the calling function. I'm main, and you're the function swap. I didn't give you 10 and 20. I gave you the buckets that contained 10 and 20. And what you did is you looked at these buckets and go, okay, great, I've got these buckets now. I'll pull out 10, I'll pull out 20, and I'll put this 20 back into that other bucket over there, and I'll take this 10 and I'll put it into that other bucket over there. Pointers are buckets because they're referencing this memory location. You can put whatever the hell you want in that memory location. That's a bucket. I put 10 in there. I put 20 in there. You can take things out of the bucket, right? You can put things back into the bucket. Right? And by the way, I gave you the buckets. They're still in my hand, right? I still know about the buckets. You might put them down on the floor or whatever, but I can still see the buckets. I didn't give you what was in the buckets. I gave you the buckets themselves. And now I can go ahead and see that, in fact, they are changed, right? 10 and 20 here. There's some additional gotchas. So, gotchas, errors, right? So in C, a pointer should or must. In C, a pointer must match the type that it points to. So what I mean by that is, consider the following. Foo is equal to 3.14, and I'll format it as C. There we go. Foo. How do I make a pointer to a double variable? I'll try to do what I did before. Int star ptr bad ptr, and I'll make it point to foo. Does that look right? Bad pointer is what? It's an integer pointer. It can point to an integer. I forced it to point to a double. Let's find out what happens. There we go. Let's go ahead and say foo contains %f. Bad pointer points to %f, and then I'll end the line, right, and get rid of all this stuff here. Right, there we go. What I'm going to do is I'm going to print out foo. That should be pretty straightforward, right? That should be 3.14 and then a bunch of zeros. But what I'm going to do is I'm going to print out bad PTR. Now, bad PTR by itself is just a memory location. So how do I take a memory location, a pointer, and change it into a regular old variable again? Asterisk or star. Right? And let's find out what this looks like. Demo. Yeah, I'm getting a warning because this is not correct, but it'll run. Bad pointer points to 0. Right? It points to a location that contains, I should say. That's what it actually is doing. Right? It points to a location that contains 0. Is that right? Nope. What's happened here? A double is 8 bytes. I've created a pointer that points to the first, not 8 bytes, but the first 4 bytes because it thinks it's an integer. That part of the number happens to be all zeros. The real number, 3.14, is down here. Right? In fact, I can show you that maybe it'll even work. Well, not even if I make it big enough, but it'll just reinterpret it. I could say bad PTR plus 4. All right. Magic for now. Let me see what happens here. It's going to print out garbage, I'm sure. Oh, it's still 0. Okay. Oh, duh. Bad point PTR equals. I'll add 4 to it. There we go. Nope, it's still printing out bad. Yep, oh well. Bad pointer points to foo. I add 4 to it. Fine, I'll add 8 to it. Nope. Give me something that... 16? Take me somewhere else, at least. Nope. Oh well. %D, maybe? Oh, because bad pointer is... Okay, there we go. Now let me go back to 4 here. There we go. Warning. There we go. Oh, I finally got garbage. That's actually not garbage. That's the 3.14, that part of the number being interpreted as an integer, which just happens to have that particular value up there, right? And it's taking the raw bits out of that thing and interpreting them as an integer. But it's doing it wrong, right? It should a double is 8 bytes, right? I'm pointing to the first 4 of them. What I did here by adding 4, by the way, is I said, here's a memory location. You're initially pointing to this memory location. Go over 1, 2, well, add 4 to it. 1, 2, 3, 4. There we go. And so point to that part of the memory instead, right? I'm just going over, and this is pointer arithmetic, but something that we'll get into later on. But you can see that you're going to have bad results if you do something like this.
So you can't add the pointer.
You can't what?
You can't add
You can add pointers, but memory address XYZ plus memory address ABC, does that have much meaning? No. But you can add values to it, like go from that memory location to 4 bytes over or 8 bytes over, right? And now you've got an array. And that's how arrays are done. But the real way of doing this is to create a proper double pointer. So double bar is equal to foo. And now you're doing it correctly, right? Double star is a pointer to a double. How would you get a pointer to a character? Char star, right? Hey, I've seen char star before. Where did we see that? Or something that looks like a char star. Char star star. Ah. So, this entire time that we've been thinking of this as magic, I wonder what it is. Now the wonder is gone. What is it? Well, maybe there's still a little bit of mystery here, because that would be a pointer, right? If I put 2 of them there, what do you think that is? To a pointer in what? Say it again.
2D.
2-dimensional pointer, kind of. It's a pointer to a pointer, right? So you've got a pointer to a pointer, so, and that points to a character. What this is doing is it ends up doing a 2-dimensional array of characters. What is a 2-dimensional array of characters? You've got rows and you've got columns. Take any one row, and what is that thing? A string. So you've got an array of strings. Right? Hello, how are you? That's how command line arguments work. Right? That's how if you were to do a.out of hello, how are you 10. Right? Each one of those is a string, 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 and this is also a string being stored as a 2-dimensional array of characters. Hello, how are you 10, etc. Yeah?
So the ARGV is used to read the arguments.
Yep.
So if you don't, well, you see you have to read the
Yeah, if you do anything else, it's let's find out. I don't even know if this will compile. argv sub 0 is equal to %s and the line. argv sub 0. I'm sure that this is going to result in some sort of a segmentation fault. just warnings though, warning, 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 warnings everywhere. Don't do this, right? Yeah, segmentation fault. Because this is not an array of strings. It's only one string. And it's trying to shove all of those into one string, one giant string. I don't know how it's doing it under the hood, but certainly trying to access them is going to corrupt memory.
So if you don't run anything?
It probably, yeah, if you don't have this, it'll probably run. You've got bad code in there that if it were to actually do anything with it, then it'll segmentation fault. But it's like you can look at the house, but if you break into the house, then that's bad, right? You can look at the house all you want, just as long as you don't go in the house to look at its contents. You can come up with a memory address all you want, as long as you don't look at the contents that don't belong to you, right? Okay. Other questions? Otherwise, we've got a little bit more on functions and stuff like that, but that basically means that we can pass stuff by reference. That means that we don't have to have any return values anymore. If I want you to compute a value, I can give you a bucket to put that value into it. That frees up this return value to do error handling. And we're going to start returning error codes. Some people have asked, what is the difference between exit 0 and exit 1? Those are error codes. 0 generally means everything went great. False. There was no error. 1 is one type of error. 2, that's an error, but it's a different type. 3, right? Well, that's yet another different type of error. And depending on the error, yes, an error happened. 1, 2, 3, those are all true. But depending on the value there, you can then start reading into it. Well, what did happen? Was it a null pointer error? Was it a divide by 0 error? Was it some other error, right? And then you can start making decisions on how to handle those things. Well, if it was a divide by 0 error, I'll do one thing. If it was a null pointer error, I'll do another thing, etc. Okay? I would be remiss if we didn't go to YouTube. Any questions? No? All right. And listen to the advice given by Bret Hart. It didn't work yesterday because I was on VGA, but I'm on HDMI, so this should work. Do I have audio? Okay. Bret Hart, null pointer. All right. So let me go back over here to my CS50 IDE, and let's get rid of all this stuff. I'll go over here to demo. Here's another bad pointer, null. Right? Is that pointing to anything right now? Nope. What if I were to try to dereference it, bad pointer, and set it equal to 42? It's pointing to nothing. Can I put 42 into nothing and expect it to be stored? Nope. So hopefully it works. Yep, segmentation fault. This is called dereferencing a null pointer. Anytime you do that, you're going to do it just like you forgot the ampersand with printf with scanf at one point, just like you wrote an infinite loop at some point accidentally, right? And eventually you're going to have a bad pointer like this resulting in a segmentation fault. Just remember Bret Hart's advice. There we go.
Come on, you guys. There it is, right there in front of you the whole time. You're dereferencing a null pointer. Open your eyes.
Whack. Yeah, there we go. So I'm going to whack you virtually on the head when you have a null pointer like that by simply posting Bret Hart's advice there. Everybody know who Bret Hart is? Anybody who know who Bret Hart is? Right, well, it was clear from the video that he was a wrestler, right? He was a wrestler from the 80s, 90s, whatever. And what that was it was a promo video for some wrestling game that was being developed. And those were the actual developers in the background, and they had the wrestlers come in and meet the developers. You know, it was just a promo thing that they then put out a video on. And so, of course, Bret Hart, debugging their program for them for the wrestling game and finding a dereferenced null pointer, right? And having his colleague whack him upside the head. Just remember that advice, right? So I will remember that for the end, to the end of my days, that Bret Hart told me, make sure to never dereference a null pointer. Right? And hopefully now you will too. If you don't know who Bret Hart is, maybe it won't be as visceral for you, but it was visceral for me because I remember Bret Hart growing up. All right. Any questions? Yeah.
So if you set a, no pointer, if you make a no pointer, what do you use it for? Can you point it to nothing?
This is not very useful, but you can check for, but it's best practice to initialize it to something. Because if I have this, it could be pointing to random memory location XYZ. But if I point it to this, then I can do a null pointer check later on. If this pointer is null, don't dereference it. If it were pointing to random memory location XYZ and I dereferenced it, right, I would have no idea, does that memory belong to me? There's no way to tell. The operating system would tell me by killing my program with a segfault.
Set it to null so that later on you're going to use it.
Yeah, if you know what to set it to immediately, then just do that, right? If I've got a variable called x and I want it to immediately point to x, then I can do something like that. But failing that, I don't know what I'm going to point it to yet, then just set it equal to null. Okay. All right, see you on Thursday then.